Thanks a lot for all of you to join me. And for the warm welcome, Joyce. Today I'm going to talk about building and validating an AI scheduling system at Singapore Changi Airport. This work was one of the key projects that I did at NTU. And so I'm going to take you through this in the next 40 to 45 minutes. So the presentation would flow like this. I'll start with explaining the airport congestion problem. Then we will formulate the optimization problem that we solved using deep reinforcement learning. After that, I'll show what happened when we put the system in front of real air traffic controllers. And finally, I'll conclude with what remains unsolved. And if time allows, I'll also delve into the future directions. But before we do that, a word of thanks to the organizations and people who made this possible. So CAS and NRF, they awarded me a PhD research scholarship. And thereafter, they generously funded my postdoc. And I'm also very thankful to these 5 gentlemen who have been through the research journey with me, Nam, Brian, Than, Michael, and Prof. Samir, who was my supervisor. So let me first set the context. Passenger numbers are expected to double in the next 2 decades. And more than 50% of this traffic would be demanded in Asia Pacific. Now let that sink in. The numbers that we have arrived at the last century, we are going to double that in the next 25 years. This is unprecedented. Increased air traffic demand without an equivalent increase in airport capacity, which is, by the way, constrained by the physical infrastructure, is expected to cause congestion, leading to delays. And when congestion becomes the norm, it would not be unusual to see 15 to 20 aircraft long queues, with aircraft spending much more time taxiing and burning fuel than they should. The image on the left is a real scenario from John F. Kennedy Airport in the US. And you can see a lot of departing aircraft waiting for their slots before they're allowed to move into the runway. So this is the specific context in which my research developed and culminated in a tool called IMATE. This video gives a brief overview of IMATE, and it nicely summarizes my research on airside congestion management.
Owing to airport airside congestion, on average, an aircraft gets delayed by 7 minutes. This, in the US alone, means $900 million lost yearly from excess fuel burn and increased emissions. Understanding the root cause of delays requires grasping the complexity of the airport airside, which is fraught with uncertainties like delayed pushbacks and unpredictable taxi times. To effectively manage congestion, we present IMATE, an intelligent departure metering advisory tool, which is data-driven and uncertainty-aware. Departure metering is an effective approach to contain taxi delays by controlling departure pushback timings. IMATE is trained to perform departure metering using a deep reinforcement learning paradigm. In this paradigm, an agent is trained to recommend aircraft startup approval times to an air traffic controller. Call it the Siri of the controller, if you will. To train, we generate actual airport scenarios using historical data. However, unlike model-based planners, we allow the agent to interact with the airport environment and learn to behave under uncertainty. The goal is that given any state, the agent should recommend actions that would maximize the reward. Once the agent's belief state has matured, we incorporate it in an interface and test it on unseen scenarios. This is an interactive IMATE interface. It is composed of 2 blocks, the flight dashboard and airside display. The flight dashboard displays arrival and departure schedules along with pushback recommendations. The airside display offers a visual overview of the traffic situation at the airport. IMATE can function in both autonomous and interactive modes. In the interactive mode, a click on the aircraft position highlights corresponding aircraft details on the flight dashboard from where pushback approvals can be issued. Remarkably, in the autonomous mode, even under uncertainties, the agent learns to orchestrate smooth traffic flow with no handholding. IMATE is able to achieve efficient airside traffic circulation at the airport. This is going to have an amazing impact. Simulations conducted with real-world traffic data demonstrate that IMATE can significantly reduce airside delays at large airports, potentially saving fuel burn with less carbon in the air. Validation experiments show that air traffic controllers find IMATE reliable and trustworthy to manage airside congestion. Overall, IMATE offers an effective way to manage congestion, leading to more efficient and sustainable airside operations.
Okay, so the presentation will be broadly divided into two parts. The first part, I'll discuss the IMATE's underlying algorithmic development. And in the second part, we'll discuss validating IMATE with human air traffic controllers. So let's start. Now, we've been hearing this word departure metering frequently now. What is departure metering? Departure metering is a surface management procedure in which departures are held onto their gates, and they are released briefly before their takeoff time to taxi to the runway and then take off. So back in the day, when the traffic levels were lower, pilots would ask for pushback and controllers would readily allow them to push back. But with time, we started seeing that as our traffic levels grew, we started seeing these queues of aircraft, basically aircraft waiting in queues for their runway slot and actually going nowhere. So the idea for metering was, this is the key idea, which is to transfer the waiting time from the taxiways onto the gates. Now you may ask, what is the benefit? The benefit is that when you don't have the taxiways clogged up and the runways can be easily accessed, the whole overall traffic flow between the arrival and departures improve. Consequently, so basically, besides the reduced waiting time, this also naturally reduces the fuel burn and emissions. So, however, if you were to look at state-of-the-art departure metering algorithms, they suffer from some limitations. Most of these algorithms are model-based, and they employ model-based control. Now, by trajectory or queue-based model, it's essentially the idea wherein you would try to forecast the future position of an aircraft 15 to 10 minutes down the line, and you would do it for all the aircraft trajectories. You would try to identify if there is any potential conflict. If there is, then you would basically work your way back and then do something now so that you don't end up in those situations. These are classic MILP formulations. And what we have seen is that these models make many simplifying assumptions. For example, the Semikis model here, it assumed that queuing only happened near the runway and not on other parts of the taxiways. So consequently, you lose a lot of spatial realism, and it fails to capture the non-stationarity that exists in the complex airside operations. And because the control actions are derived from fixed model parameters, these policies prove brittle under uncertainty. Badrinath here actually showed that when you expose these models to uncertainty, the promised benefits actually reduce by 50%. And also, we have seen that these algorithms and models don't scale. So to overcome these limitations, we try to adopt and choose a data-driven simulation-based optimization technique. The idea is simple. You have an agent, a neural network, which basically interacts with the environment. It sees the environment, does some action on it, gets a feedback if it did well or if it did worse, and then it tries to improve its weights so that it does better next time. We take inspiration from the domain of road traffic signal control, where deep reinforcement learning has recently attracted a lot of attention. And the recent work has shown that the learned policy can scale with traffic density. So to formally put it, the research problem that we asked ourselves was, can a deep reinforcement learning based departure metering policy effectively reduce taxiing delays while maintaining runway throughput? And the decision scope that we have is only the target startup approval times, or the TSATs, the pushback schedule of departures. So the challenge here is the fundamental trade-off. Holding aircraft at gates reduce taxiway congestion, but it risks starving the runway of traffic. On the other hand, releasing too early maximizes runway pressure, but it creates long queues. So the agent must find a middle ground. And to perform simulation with optimization, we need a simulator. So we developed it in-house. We generate scenarios, and to generate realistic scenarios, we derive the actual data, and then we probe it for the surface movements. We take the start times, the routes, the intended routes of the traffic, and the traffic mix for the day. Then on top of it, we introduce operational constraints, like some routes can only be traversed in a certain direction. So we introduce these operational constraints and sources of uncertainties to generate realistic scenarios. And then after we have generated the scenarios, we calibrate it against the historical data to see if we were doing calibratedly well. Now, to learn a deep reinforcement learning based departure metering policy, we need to define a Markov decision process. This is how we do it. It's a high-level overview. We basically have a simulator environment. We run that, and we extract vectors, and we feed this information that we see from the environment to the departure metering agent. We need the agent to perceive broadly two kinds of things. First, where the traffic is currently now, and where is it heading. For each aircraft, we encode its current position, its speed, its assigned route, and the word here is route flow. So we cluster similar looking trajectories into dominant flows, and then we feed this information. We also feed the runway availability, basically time until the next slot opens. And one of the novelty here was we encode traffic density in hotspots. So hotspots are basically cluster of intersections where conflicting movements can cause delays. This feature gives a compressed spatial picture of congestion. Then, after seeing the observation, the agent has to decide whether to hold the aircraft or to release it, and it does it for all the terminals. Based on the action taken, we feed it back a reward. Now, this reward might look a bit complex. Let me break it down. At the higher level, the intuition is that we want to penalize taxi delays and we want to incentivize the runway utilization. So the reward is a combination of three things. We call it R taxiway, R pushback, and R runway. And we did this. We did some ablations to see what would happen if we would not have one of the components. So if you don't have a R taxiway component, basically which was this linear expression, you would release everything because you don't penalize slow moving speeds on the taxiway. What we then saw was long queues and delays. If we were to remove the pushback incentive that we give to the agent does not push back at all because of the nature of the reward, how it is set up. Just releasing the aircraft starts to move slowly until it finally reaches its top speed, its free moving speed, free flowing speed. Until then, it accrues negative rewards. So a reward of 0 was better than negative rewards, and therefore you would see empty vacant runways. And when you would take away the runway component from the reward, you would see that the throughput would not be very high as in the case when you have all the three reward components there. So it's a very high level understanding of how rewards were decided. And then the coefficients that you see here were all decided by trial and error. So there's a lot of reward shaping that went into this. Now, let me talk about, before we go to the experimental design, once we have set up this MDP, what we do is we then train a deep reinforcement learning model. In this case, we took a proximal policy optimization model. It was a standard implementation by stable baselines, but then we fine-tuned it to our problem parameters. And then it took some days of work, but then it was not a very different in that sense. So to talk about the experiments, we will do 3 sets of experiments. The first set would be on the usual traffic density scenarios that we see at Changi, which is like 40 aircraft movements per hour. We would measure the aircraft taxi out delays, taxi out times, and conflictual interactions with and without metering, with and without our model. Then we would vary the traffic to see if the model scaled to high traffic density scenarios. So then we would measure the average taxi out time, and then we would also measure the runway throughput. And now we would benchmark it with other state-of-the-art algorithms and the standard MILP formulations that you would solve using any meta heuristic. Finally, we would measure the performance on the entire day of operations. And then we would compute taxi out time, gate holds, and fuel burn. This is how the results look like. So with metering, you see the white bars are the, so on the x-axis, you have taxi out time in minutes, and on the y-axis, you have the probability. So you would see that the distribution shifts leftward, which is a good thing. The mean reduces by almost 44%. And consequently, because the delays reduce, we also see the overall taxi times, the average taxi times also reduce on average by 2 minutes. Now, one of the cool results is that the reduction is because of the conflictual interactions, reduction in conflictual interactions. So you can have basically 3 kinds of conflict on the airport. First is a following conflict, wherein an aircraft is, because of the aircraft in front, has to impede its movement. So, and then crossing conflict is when 2 aircraft are approaching an intersection and one of them has to give the right of way to the other. And the third is the head-on conflict. We see that with the metering, which is the blue bars, we could see a reduction of almost 3 times, 3x drop in the following as well as crossing conflicts. The head-on conflicts didn't reduce as much, but there was nonetheless some reduction. For the second set, when we vary the traffic density, now I think I did mention, but it's good to mention again that the red bars are the non-metering scenarios. DRL, the blue one, is our model. MORI is another state-of-the-art simulation-based optimization model. And GA is the MILP model that we would formulate, assign an aircraft, pushback times, given that you want to minimize the taxi delays and you want to constrain the runway throughput drop, and then you expose it to the uncertainty. So this is a search-based method. So we saw that the non-metering taxi delays are the highest. So you have a taxi time on the y-axis and the number of aircraft in the scenario on the x-axis. We see that all the 3 models, DRL, MORI, as well as genetic algorithm, they show reduction. But on average, the deep reinforcement learning model is able to contain the delays the best, especially in high density scenarios. For runway throughput, we expected the model to not do any better than non-metering case, because non-metering cases is the ideal thing for runway throughput. You basically release every aircraft and any aircraft whenever they are ready. So you have maximum pressure on the runway, but then you have long queues as well. So the metering would have done the best. DRL is able to recover 98% of that best, of that ideal scenario, and others a bit lesser. For the third set, we have hour of the day on the x-axis. The bars represent the departure demand for that hour, and the line plots are basically the taxi out time and gate holds. So the solid line plots are representing the taxi out time, and you see a drop in the runway in the taxi out times with metering, which is the blue plots, and that drop is basically transferred as gate holds. So metering is able to basically reduce the taxi delays by transferring waiting time at the gates. And consequently, we also see that less delays translate to less fuel burn as well. With metering, we are able to observe a 22% reduction in fuel burn. So far, we have discussed that in usual traffic density, we saw that the deep reinforcement learning model could reduce the delays by 44%, which basically meant 2 minutes savings per aircraft. It could reduce the fuel by 22%. And we also saw that the policy scales well with traffic. So now I'll move on to the second part of the presentation. But before I do, I'm happy to take any questions.
Your throughput. Surely the throughput in terms of plane takeoffs per hour is like planes scheduled per hour. It's planes, you can't get new planes or lose planes,
Yep.
right? So if you need 40, if you've scheduled that many, that's kind of, so how can throughput be something that's not?
So there is uncertainty on the airport surface. We have a schedule, but it is rarely followed.
But in the long run, the plane's not, it has to take off, right?
Yeah. But then we are looking at the duration that you would need to depart that many aircraft.
Okay.
So because there are delays, the aircraft would reach late. And therefore you would serve the same number of aircraft in a longer duration. So per hour, the throughput would drop.
I see. It's a more trend.
Yeah, we normalize it.
Yeah. Okay.
Yeah.
Under some circumstances, an aircraft will be cancelled.
Well, yeah, but that's not.
The same throughput across 24 hours.
Yes.
Yeah.
But if you're talking about like during busy time, per hour, then you will see the difference.
I mean, I would add to that, like maybe even, so if you're looking the whole day traffic, so it's just a matter of, how many aircraft you can serve in less time. So the extrapolation is that if you can serve less aircraft in 1 hour, if you would extrapolate to the further throughout the day, you would also we see that a lot of aircraft miss their slots because they're not able to reach the runway in time. And therefore then that piles up and therefore the time increases.
And my other question is, are you going to talk about the effects on gate congestion, right? Because now they're spending longer at the gate.
In this talk, I'm not done that, but there's a follow publication, and I can share the publication with you, wherein we did analyze the effect of pushback on the gate operations, especially the passenger movements, and how much of that affects the passenger itineraries in terms of misconnections. Yeah.
I've got a good question. In terms of the delay, so we got taxi delay and gate delay. Of course, I understand the gate delay, there's no fuel burn, right?
Yeah.
So would that be a simple conclusion saying with the metering, the sum of the delays is larger or greater than equal to?
The sum of what delay?
So the sum of taxing and gate delays is greater than equal to the sum of taxing and gate delays in the no metering environment.
Yes. No. I think so. It's very important to define how we is to state how we define delays. We define delays as a no delay situation is an aircraft starts to move from the gate, reaches the runway unimpeded. That's the best case scenario. And anything above that is a delay. So we define delays in terms of movement. Now, gate delays, we call it gate holds. So it is by design, we hold the aircraft. So we don't call it a delay. But if you were to look at outside the airport, yes, that would mean delay. But the overall idea is that even if you were to release that aircraft, it is not going outside the airport because it is stuck inside the congestion. And so we don't call it delay that way. Any other questions?
This question is based on the Singapore Airport.
Yes. So in part one, we saw that IMATE operated autonomously, but in practice, IMATE doesn't work like that. It works as a decision support for air traffic controllers who are the final decision makers. The fundamental challenge is that the effects of pushback approvals are realized much later, typically 10 to 15 minutes of aircraft taxiing to the runway. So air traffic controllers or ATCOs, like we call it in the domain, mentally simulate future airside state to evaluate whether a pushback is good at this time. Cognitively, it is demanding to consider uncertain runway traffic forecasts. And this is the kind of long horizon reasoning that the DRL agent or the deep reinforcement learning agent is good at. So now the question then becomes, will the controllers trust the system enough to follow its recommendations? So we took 7 professionally rated controllers. 6 of them were male, 1 of them was female with 2 to 10 years of experience. Let me be upfront, this is a small sample. And this is an exploratory study, not a controlled experiment. So the results that we have are basically qualitative insights into how controllers interact with AI-generated advisories. The setup was the taxi routes are pre-assigned. So the aircraft can't change routes midway. And air traffic controllers manage the conflicts via mouse clicks or keyboard strokes, which is different from how it happens in reality. In reality, they have to talk over a frequency to the pilots, but this was a simplification. So the sole task, which is like intentional of the controller, is pushback approval, because we deliberately wanted to isolate this decision to study it cleanly. And we basically present 3 scenarios to every controller. The first scenario is for them to familiarize themselves with the tool, with the traffic, and basically ask any questions that they had. And scenarios 2 and 3 only we use for evaluation. A typical scenario works for 20 minutes, wherein, this is maximum, by the way, controllers would finish before that. And we use this configuration at Changi Airport. So the arrivals would move in this direction, which is runway 2L, and departures would follow this configuration, which is runway 2C. Now, let me also talk about the scope objective of this experiment. So we have air traffic controllers that are tasked to approve 10 departures from the respective gates. And the task for them, like one of the questions was, we want them to do it as quickly as possible without accruing delays. And then the objective for these experiments for us was to ascertain the adherence, the efficacy and acceptability of IMATE's recommendations. And we would do that by first measuring the throughput, the taxi out delays, and also the feedback from the controllers. We use these forms for the qualitative feedback and to understand how the situational awareness of the controllers were during the whole experiment. So first, some qualitative behavior that we saw. So I'm not showing you the schedule, but I'm just showing you the traffic movements. So you have in the background Singapore Changi Airport, the map. The green icons are the departing aircraft for the day, and they are positioned on the gates. So whenever an aircraft is ready to push back, the icon would appear. So we saw that air traffic controllers have their own ways of working around, and we saw that they optimize locally. They clear aircraft from one zone here, and then they move to the next. And this is actually consistent with how they are trained to focus on one zone at a time, because there are multiple controllers who would manage different zones. So it is how they are trained. But IMATE is trained to look at the whole traffic globally at all the terminals simultaneously. So the first was this spatial observation, and the second one was the temporal observation, which was that air traffic controllers tend to default to first come, first serve. If an aircraft is ready, the instinct is to release it immediately. Even if the IMATE recommends it recommends holds on that aircraft. IMATE sometimes resequences the departures to serve the global objective, which sometimes conflicts with controllers' fairness heuristic. As a result, what we see unfailingly in almost every case, that when the controllers are not following the advisories, they would end up in situations when they are not able to perfectly predict how the situation would look at the runway 15 to 10 minutes down the line when they are allowing the pushback decisions earlier. So it's very common to see situations wherein the aircraft are just waiting before the runway and there's a queue. And IMATE was trained to have sufficient gaps between them. And sometimes before the want of the sufficient gap, because of the uncertainty, it would miss a slot. And that was the trade-off that it has to, settle on. So on the quantitative side, we first measured how the compliance looked like. And this study actually reveals, so by the way, the y-axis is the pushback deviation. It's a proxy for compliance. So if the aircraft is released too early or too late, that means the pilot was not complying with the recommendations. Whereas if it is too, if the bar plot is too small, then that means that the compliance was very high. So first of all, we see that there's a very nuanced and intricate picture of human behavior when it comes to following advisories. Air traffic controllers, DNG, they adhere completely, but C, partially or not at all. But overall, in the second scenario, on average, we saw that, it demonstrated to us that on average, a higher degree of compliance was within the second scenario. And now this is taxi delays and runway throughput. On the left is taxi delays on the y-axis, and each air traffic controller plotted on the x-axis. We observed two things in the left plot. First, that like in the previous plot, compliance in general was higher, and then average taxi delays were 25.6% lower. So the red bar is scenario 2 average, which is lesser than the scenario 1 average. Now I want to be a bit careful here. This is not an observation. This is basically an observational correlation. It is not a controlled causal study, but the pattern is suggestive that congestion in scenario 1 appeared. It actually made the controllers trust the IMA's recommendations more in scenario, because they experienced heavy congestion in scenario 1 when they were not following the advisories. And this is basically consistent with what we know in psychology, what we call learning or adaptation effect, wherein experiencing the cost of ignoring a tool may increase a subsequent reliance on it. Because of the in scenario 2, but we also see a drop in runway throughput. It is a modest drop, but drop nonetheless. So when we look at the feedback from the controllers on all these experience of theirs going through these experiments, we saw that usefulness, reliability, and accuracy, they received high ratings across the controllers. So you basically have a scale of 1 to 7, and most of them would basically rate it between 6 to 7 on a 7-point scale. Transparency received the lowest scores, and which was kind of expected, because you can't really explain, or at least inherently neural networks are not understandable. Controllers basically wanted to understand why IMA recommended a particular hold time. And so this interpretive challenge is there. And very surprisingly, not surprisingly, but like reassuringly, the IMA was rated high on situational awareness as well. We don't want the controllers to lose their situational awareness and depend too much on the automation. So they could retain it through. So you would see an average of, or mostly the ratings are around 8 or 9. So in conclusion, we saw that the algorithm works. In simulation, the results are strong and they scale, but putting humans in the loop changes the problem fundamentally. Controllers actually bring their spatial heuristics, their fairness preferences, and the risk attitudes that interact with the algorithm's recommendations in ways which are difficult to fully anticipate. Higher compliance was associated with better outcomes, but compliance itself is a function of trust, transparency, and individual differences. So the throughput was a cost that they had to pay for lower delays. Now, in terms of unsolved challenges, there are a lot. I just listed 2 here. One of them is certification. The idea is, how do you certify a neural network? How do you certify AI-driven algorithms, especially in safety-critical contexts like ATN? It remains an open challenge. And then we also have individual differences between controllers. So one-size-fit-all policy may not get all the buy-in from all the controllers. So this is something that I can talk about a bit in the future directions, but I think for now that was the core of the work that was done. So if anyone has any questions, please feel free to ask.